Okay, so let's talk today about reflections first. Okay, so reflections. And I gave you this handout. Everyone have this still? Was anyone absent Friday? Maybe you didn't get one of these. Or maybe you lost it. I have extras. You need it. Take it out. Gotta have it. Yes, you need one? Fair enough. Okay, so reflections. Right now, for us, there are two reflections we're interested in. One is reflect over the x-axis. And when you reflect something over the x-axis, its coordinates would change from something like AB to be this point down here as an image. So we have an image and a pre-image. So when you do that reflection, any points at AB are going to go to A negative B. And if there's a point at A negative B, it's going to reflect up to go where AB is. So that's our reflecting over the x-axis. I told you in this class, we probably will use A and F of A, right? So let's use that instead. Instead of writing B, we'll write F of A, see? Okay, so what I'm saying is whenever we multiply F of X by negative, it's going to turn upside down. An object will turn upside down. So y equals negative F of X. This will cause it to look upside down. Just like the happy face I had earlier. Okay, the other option is we can reflect over the y-axis. So a point like AF of A would end up over here at negative A, comma, F of negative A. See? Negative A and its function value accordingly. Okay, so y equals F of negative A. F of negative X would be our reflected graph over the y-axis. Y equals F of negative X. So these are not the same thing. This would mean backwards. So you think sometimes students might get these two mixed up? What do you guys think? Negative F of X and F of negative X? Yeah. Okay, one of the confusions is sometimes they're actually the same thing. But in general, we don't want to think of them as the same thing. All right. So I'm going to do an example where they are exactly the same thing. Okay?
How would we tell?
You'll see. So my first example is this. If y equals x cubed, or actually I'm going to write f of x equals x cubed, if you don't mind. So f of x equals x cubed. Then I want to graph f of x, f of negative x, and negative f of x. Okay? So we're going to graph both of these. Okay, you're supposed to know this graph now. This is x cubed, so you're supposed to be very familiar with it. It passes through 3 points, 0, 0, 1, 1, and negative 1, negative 1. So it looks like that, right? And then we're going to be trying to graph for part A, f of negative x, and then for part B, I'll do that in green, negative f of x. So they're not the same, generally speaking. All right, so let's graph this here. F of negative x means flip it backwards, right?
Thank you.
Okay, so let's draw this backwards. So if you do a right-left switcheroo, where left becomes right and right becomes left, this point right here, let's call it point A, is going to end up over here now. A prime, right? And this point, let's call it B, is now going to flip over the y-axis and end up over here. So this might be point B prime. See? The only point that's not going to move is the point that was at 0, because if you flip it over the axis, it's still at 0. So your graph is going to look like this. Just rough sketches. Okay? Now let's flip it over the other axis. So this one, let's go ahead and title it, it was reflect over y-axis. So what would happen if I reflected it over the x-axis? Okay, so point A is not going to be down here. Because it reflected over the x-axis. And point B is over here. And the origin point, that didn't move. So this is a very rare situation, but I reflected over the y-axis first, and then I reflected over the x-axis. And they look exactly the same. I reflected over y-axis, reflected over x-axis, same exact graph. This is very unusual and very rare. Why did this happen? Why would f of negative x be the same as negative f of x? Do you guys remember what we said last week about this? This only happens with what kind of functions? Odd functions, yes. This is a characteristic of an odd function. That's why I picked this example. Y equals x cubed is an odd function. It has origin symmetry. So when I did the two reflections, lo and behold, they're exactly the same. So this is a visual confirmation of the definition of an odd function. See? We see the graphs are identical, and we believe it even more now. So recall, f of negative x equals negative f of x is true for an odd function. But why did this happen? We say that f is odd here because this happened. But why did this happen? Let's look at it. So let's just look at it from a non-graphical perspective, right? What does it mean to write f of negative x? What does that mean? It means to make all of your x's, what? Negative x's, right? Okay, so if f of x is simply x cubed, f of negative x means to replace the x's with negative x's. That's what it means. What does this simplify to? Negative x cubed, right? Because negative x times negative x times negative x is negative of x cubed, right? And what does negative of f of x mean? Right, this just means take the opposite of f of x. Well, what's the opposite of x cubed? Negative x cubed, right? So this is our minus now. But it's the same expression. See? So whether you change x to a negative or just negate the whole expression, we get the same answer and hence the same graph. So this is a special case. I'm going to write that on here because I don't want you to think that every time you do the reflections you get the same result. Okay, now let's just do another example where it doesn't work quite that nicely, you know? All right, so my second example I picked was y equals, what did I pick? Absolute value of x. Okay, y equals absolute value of x. So you guys know what it looks like? This is our parent function. It's on your note card, your flash card. So we're going to graph f of negative x and negative f of x. So I'll title this f of x again. Okay. So the first one, remember, means to draw it backwards. Well, this one is interesting because if you draw this graph reflected over the y-axis, it's going to look identical to what it looks like right now. Right? You can follow the 3 points if you want. So this was the point A and this is the point B. Right? They're at 1, 1 and negative 1, 1 respectively. But when you flip over the y-axis, they just trade places. That's all that happens. So this is your point A prime and B prime. So your graph is literally backwards. Not very interesting. So this is reflect over the y-axis. For part B, we reflect over the x-axis. That's our upside down operator, right? When you have the minus out front. So that is going to look different. That's going to look like this, obviously. Point A here, point B here. Upside down is not the same as backwards on this particular example. Do you guys remember what we wrote on our note card when we did the odd even descriptions of our flashcards? What did we put for the absolute value function, remember? Yeah, it was an example of an even function, which means it has y-axis symmetry. So no wonder when you flip it over the y-axis, it looks like it used to. Right? Okay. So we can write that here as well. F of negative x looks identical to f of x for an even function. So what's happening mathematically here? Well, if f of x is absolute value x, what does it mean to do f of negative x? It means to change your x's to negative x's. So let's see what happens. What happens here? Well, what's the absolute value of negative x? It's not x.
It's positive.
You got to be careful here. The absolute values will wash away the negative, but it will not be removed from the problem. So it's going to be absolute value x. Absolute value x is the correct answer to my question. This simplifies to absolute value x. It does not go all the way to x. Because the output of this has to be positive, right? Absolute value of anything comes out positive, or 0. If you just go all the way to x, and x is a negative number, then something's wrong. So you can't take away the absolute values, but you can wash out that negative. Okay, so that's what happens when you find f of negative x mathematically. What happens when you do negative of f of x? That just means multiply the function by a negative out front. Notice these are not the same, right? They're not the same. We have absolute value of x and negative absolute value of x. That's why the red and the green graphs look different. And if I had to match up two of these and say they look the same, I would say the original parent function, f of x, looks just like f of negative x. So the red and the black match this time. That's the definition of an even function. And this is the mathematical reasoning. This is f of x. It's the same thing you started with. So I'll just go string this together and put equals f of x. So f of x and x of negative x are indistinguishable. Does it bother you that absolute value of negative x is not x? Is it bothering anyone still that absolute value of negative x? You cannot just change that to x. Raise your hand if that's bothering you. Okay? We'll see. All right, so we saw an example of an odd function, and we flipped it both ways, and it looks identical. We saw an example of an even function, where the y-axis reflection looks just like the original problem. Do you think it's possible to have a graph, and it's a function, and then you flip it over the x-axis, and it looks just like it used to? Can you draw one on your paper? Let's try it. I would like you to draw a function, and when you turn it upside down, it looks identical to the way it does now, like before you flipped it. Before and after. Flip it upside down, it looks just like it did originally. Try it on your paper. Let's see what you guys come up with. Trying to draw a function. You flip it upside down, it looks just like it used to. Try it on the paper. And when I say it looks just like it used to, I mean it is the exact same graph. It's not in a new place either. It's in the same place as it used to be also. I'm not taking questions right now. I'm asking you to draw something on your paper. When you flip it over, it has to look just like when you started. See? And it has to be the exact same spot. Because we've seen odd, we've seen even. Is there like a third category? See what I'm saying? Yeah. You have an example? Okay, so Jason, what's your example? No. When you reflect it over the x-axis, it is indistinguishable from the graph you started with. Yes. Yes. Y equals 0. Okay, let's look at y equals 0. So y equals 0 is also known as f of x equals 0. F of x equals 0. What does that look like? That is the y equals 0 line. So it's this line right here. It is the x-axis. Okay? So what happens when I flip it upside down?
It is the x-axis.
It stays right where it's at. Right? So if you reflect it over the x-axis, it is completely indistinguishable from the original function. Did anyone come up with anything else? Okay, you should have trouble coming up with something else. Because anything you try to draw that can be reflected over the x-axis and maintain its original look would have to be a non-function. Because it has to have x-axis symmetry. When we flip something upside down and it looks like it used to, it's because it had that as a line of symmetry in the first place. Okay? So right now, for most people, if you draw a line right down the middle of their face, right, and you switch the left and the right side completely, it'd be really hard to tell that that had even been done. Unless you have like a freckle here and not here, If there's an asymmetry somewhere, you'll spot it. But for a person whose face is perfectly symmetric, switching left and right you could never tell, right? Upside down, in this case, but we're talking about not left and right switching, but up and down switching. If you do this, and you turn upside down, it looks just like it used to. But that's not a function. It doesn't pass the vertical line test. So it's really hard to draw something that has x-axis symmetry and call it a function. You guys see the problem with it? Like you could draw something that has x-axis symmetry. If you turn this upside down, it looks just like this, but it's not a function. So this is a special case. F of x, f of negative x, negative f of x, they're all exactly the same. But it's very, very rare. Doesn't work for any other functions. We will study circles later, but they're not functions. Very special case. Good. Did anyone else think of that line? It's the only one. It's the only possible thing. So last week in the video, I said there is no such thing as a function that is both odd and even. This is the only exception. Okay, so that statement was a little too absolute. This defies what I said. This thing is odd and even. It has y-axis symmetry and it has origin symmetry. Okay? All right. Okay, let's practice dilations now. So dilation is a little bit harder. And I just want you to remember that in math, dilate means stretch or compress. Okay, so you might think dilate means to get bigger. Maybe that's true if you're an optometrist and you're talking about the human iris or whatever. So, just not the, or the pupil, I mean, that's not the case with math. It can be stretch or compress. All right. So there are 4 possible stretches that we do. We do horizontal stretch, horizontal compression. We do vertical stretch and vertical compression. So just those 4 right now. All right, so let's talk about the first one. If you see f of ax, and a is a number between 0 and 1, this is a horizontal compression. Okay, for example, if you see, I meant to say horizontal stretch. An example would be like this. Let's say you had f of x equals f of 1/2 x. Now your logic would tell you, look, if there's a 1/2 x, then the x's are going to get skinnier, like smaller, right? But actually the exact opposite is true. X's will get longer and bigger, like lengths will get wider. And so the graph is going to stretch out horizontally. Here's a graph for you. Let's say you had this function. Just a little function here. Maybe you've seen it, maybe you haven't. Doesn't matter. If this is the graph of f, the graph of f of 1/2 x is basically twice the width. So what do you get if you take 0 and you multiply it by 2? What do you get? 0. That's correct. What do you get if you take pi and you multiply by 2? 2 pi. Good. What happens if you take 2 pi and multiply by 2? You get 4 pi. So the new locations of these 3 black points are where the 3 red ones are. At 0, 2 pi, and 4 pi. So the graph would look like this. It is wider than the original. Even though half, you'd think something would be getting smaller. It's counterintuitive. Interesting. Okay? Let's do f of ax, where a is a number bigger than 1. So when I say bigger than 1, I mean like 10/9 and 5/3 and 1.2. Okay? Anything bigger than 1. 16. All right? So let's draw a graph for that. This will be a horizontal compression. So let's do f of 2x. 2x sounds so wide, you know, double the width, double the x's. It's going to get narrower, actually. So the graph is going to go from 0 and pi and 2 pi. We're going to divide everything by 2. So if I divide 0 by 2, I get just 0. So that point doesn't move. What happens if you divide pi by 2? You get half pi, right? Or we just call it pi over 2. So that's going to go here. Right here. Pi over 2. What happens if you take 2 pi and divide by 2? You get pi. So the 3 dots are here now. It usually suffices to keep track of just 3 points. There's your graph. It literally looks like a compressed spring. So it was completely squished inward toward the origin, see? Yes?
Wouldn't it go above 1?
No.
Doesn't?
Yeah. So, okay, I want to pause here for just 1 second and say something about your previous background with this dilation thing. Okay, so I'll pause the recording. Let's go on to our examples of vertical compression and stretching. Okay, so let's do this case. F of x times a, where a is between 0 and 1. So a is like a half or whatever. This is a vertical compression. So this is the original graph. Passes through 0, pi, and 2 pi. If you were to try to graph y equals 1/2 times f of x, which is the case we're doing right now, half on the outside, this is a vertical compression. So how does this work? So the idea is, remember f of x is another name for what? Y, right? So this is supposed to be read as half y. So any y values on this graph will be diminished by a half. For example, this distance right here is 1. What's half of that? Half, right? And I would say that this point right here has a y value of a half. What's half of that? A fourth. See? So all the y values, you multiply them by half, and the graph looks more like this now. The highest point is only 1/2. And this point down here, which was at -1, what's half of that? -1/2. See? So the graph just basically got stomped and crushed toward the x-axis. That's what happens when you put a half in front. Your Algebra 1 teacher says it looks wider. Really? Wider? I don't think so. Not wider. It's shorter. Multiplying by a half doesn't make things wider, it makes it shorter. Okay, on the outside like that. Let's look at the last case, and that's a times f of x, where a is bigger than 1. For example, if you wanted to graph y equals 2 times f of x. So I always draw the original so you can compare them. 0, pi, and 2 pi. Three big black dots there. This goes up to 1, down to -1. If you're going to do the 2, multiplying by 2, this means 2y. So all of the y's are going to get doubled. And so it's going to end up being twice as tall. So it's going to basically go not to a height of 1, but a height of 2. Like that. And not to a depth of -1, but a depth of -2. I find this a little hard to teach. Okay, I really do. Because all four graphs look very similar. Okay? The first one we did was the horizontal case. So what was happening was the domain was changing. It was either getting stretched out, instead of going from 2 pi, it was going all the way up to 4 pi. And then we did the case where it was squished inward. And then we did the case where it was squished downward and then squished upward. But they really are all different mathematically. So these are the four cases. Okay, so we have translate, reflect, and dilate. I taught them to you in those orders because that's the easiest way to understand it. If you were to graph a problem that involves multiple transformations, you want to reverse that order and graph using the rule DIRT. Let me show you what DIRT means, okay? DIRT means, and DIRT here is spelled DRT. D means dilate first. And R means reflect. And then T means translate. This is just a good rule of thumb if you're dealing with a problem that involves multiple transformations. You want to dilate first, before you leave the origin. Dilate, do your flipping, and then finally move away from the origin. So let's try an example of this. So let's say you're given this problem. And this is kind of cold turkey now. They're just going to give us a function, y equals -3 over x minus 2 plus 1. You're supposed to graph this thing. You can make a table if you want to, but the instructions say using transformations. So here's what you need to do. You need to first try to write this thing as a transformed parent function. So you have to identify what parent function you think it is. So what is this thing? Is this y equals x? Is it x squared? Is it x cubed? Is it absolute value x? Is it 1 over x? Like, what's the closest match? Think flashcards, which one does it resemble most? 1 over x, right. Okay, so this is a 1 over x function, and it's just been modified significantly. Okay, so first identify your parent function. It's usually not that hard to do, because you only have 10 choices, right? Okay, now you got to try and write it so that it is written as sort of a stage-by-stage sort of thing. So, first of all, are there any dilations going on? Dilation would mean you're multiplying by a number at some point in time. Yes? Yes, there's a 3 going on. See that 3? Maybe it would help if I wrote it like this for you, okay? What if I wrote it like this? Negative 3 times 1 over x minus 2 plus 1. Now that I wrote it that way, you see how my function is being multiplied by a 3? The function, 1 over x, is being multiplied by a 3. That's a vertical stretch. Okay, so let's start identifying what's going on here. Okay, so this is a vertical stretch right here, because 3 is bigger than 1. What is that going to do? What's that minus going to do? So does this look like f of negative x? Or does it look like negative f of x? The negative on the outside, right? It's not like there's a negative x right there. There's no negative x. This is just a regular x, right? So this must be like upside down. See? So that means reflect over the x-axis. So let's record that. Okay, so we talked about the 3, we talked about that negative. What does it mean to have an x minus 2 in a graph? What does it mean, x minus 2? Yes? Yes, this means shift to the right 2. So there's your translation, see? And what does it mean to have 1 added to the end of your function? Shift up 1. So for a person who knows what 1 over x looks like, this problem is merely an example of moving it around and stretching it and reshaping it. Any 6th grader can make an XY table and solve and plot the points. That is not what I want you to do. Okay? I don't want you doing that. Or you'll be stuck forever in table land. Okay? We don't want to do that. So let's try our hand at this. So we know the graph for 1 over x passes through this point 1, 1, and negative 1, negative 1. Okay? I would keep track of these 2 points. Okay? In fact, I'm going to write down the coordinates. So this is the point 1, 1, and negative 1, negative 1. I also want you to remember that there is a horizontal asymptote right here, and a vertical asymptote right here. And when it comes time to graph, we're going to follow the following stages, dirt. We'll do dilation first, then we'll do reflections if there are any, and then we'll do our translations last. Okay, it's really important you do your translations last, or you can actually get the wrong graph in the end. Really important. I don't know if the book explains that or not, but it's important. Okay, so what was my function? Let's see. I was supposed to do a vertical stretch, right? That's a dilation. Okay, so let's take care of that right now. Okay, so let's graph y equals, this is y equals 1 over x. We're going to graph y equals 3 over x first. Just going to dilate. That's it. Okay, so what happens? The point 1, 1 becomes the point 1, 3. And the point negative 1 becomes the point negative 1, negative 3. Nothing else changes. The points just sort of move further away from the x-axis. That's our first stage. Dilate. Next is reflect. Which axis did we say we were going to flip it over? We said the x-axis, right? We already identified all the transformations for this problem. Okay, so next is to do y equals negative 3 over x. I know it's hot in here. I lost some of you. It's just a little hard to learn on your own. Sorry about the temperature. I have no control over it. Okay, so what's happening now is we're flipping it over the x-axis. So that point that was on the first quadrant, in the first quadrant, is now here. And this point's here. So these branches basically switched positions. There's still a horizontal asymptote here, and there's still a vertical asymptote here. That hasn't changed. Okay, so we took care of our dilate, we took care of our reflect, now it's time to translate. We said it was basically right 2 and up 1, so I think we could draw the rest of this graph in just one more stage. Here's the right 2 and the plus 1 written in. So I want to remind you that we have, these are the points we have kept track of so far. We have a vertical asymptote at x equals 0. We have a horizontal asymptote at y equals 0. We know that the point 1, negative 3 is of interest, and we know that the point negative 1, 3 is of interest. Okay? We got to shift all of these things to the right 2 and up 1. Okay, what happens if you take the vertical asymptote and you shift right 2? It's going to go over to x equals 2. All right, so let's move that first. I like to move the asymptotes first. There we go. What's going to happen if we shift that line up 1 now? It's just going to look the same, right? If you move this up a space, so don't need to worry about that. The y equals 0 line was a horizontal asymptote. When you slide it to the right 2, you can't tell. But when you raise it up a space, you can certainly tell. So that is now at y equals 1. So my asymptotes are now at y equals 1 and x equals 2. See? They're not on the axes anymore. What happened to the point 1, negative 3 and the point negative 1, 3? Well, those guys are going to get 2 added to their x and 1 added to their y. That's how they're going to move to the right 2 spaces up a space. Okay, so this is going to become the point 3, comma, negative 2. And this is going to become the point 1, comma, 4. I added 2 to the x and added 1 to the y. Okay, so we got 2 brand new points to plot. 3, negative 2 is this point. And 1, 4 is this point. And the branches just follow. This is the answer. You can verify it on your graphing calculator, but we used transformations to graph this function. First I dilated by 3, then I flipped it upside down, then I removed it right 2 and up 1, the asymptotes move with. This is a really important example.
For this particular graph,
Yes.
would it have made a difference if you reflected across the x or the y?
It does after translation. My next example has a y-axis reflection. So I'm going to do one more. Okay? I know this is a lot of lesson, but this is a really important lesson. So this is my last example. Can you graph y equals square root of 1 minus x plus 2? Okay, so what's my parent function? You got to identify that first. Yeah, probably just the root x function, right? So I'm going to try to write it like that. How about I write it like this? Let's write it as square root of, and then we'll have negative x plus 1. That's the same thing as 1 minus x, right? Plus 2. So I think that negative x means it's going to look like backwards, right? Backwards. We said negative x means backwards. Left and right switch. The problem is I'm not used to adding 1 to negative x. I'm used to adding 1 to x. That means like left to space. So I'm going to factor out a negative like this. Okay, now I think I understand this. What it's saying is we're going to draw a radical graph. We're going to reflect over the y-axis. This means right 1 space, and this means up 2. So I had to write it in a way I understood it. I don't know what negative x plus 1 means. So I factored out the minus, and now I can see it. Oh, there it is, x minus 1, that's right 1 space. Okay. So we're supposed to follow the dirt order, right? But there are no dilations on this problem. I never multiplied by 3 or anything. So we're just going to go straight for reflections and then translations. Here's the original parent function. It's the helicopter. Passes through 1, 1 and 4, 2. That's the original. We're supposed to reflect this over the y-axis. So we all know what that would look like. So this is y equals rad x. Now I'm graphing y equals rad negative x. So that's just the helicopter flying in the wrong direction. Contains the point negative 1, 1 and negative 4, 2. And then I'm supposed to go right 1 and up 2. So you can just achieve that by adding 1 to your x and 2 to your y. And you've already got a couple points there. Okay, so it's going to be y. This is our final image. You're going to go right 1 and up 2 from where you got right now. So if 0, 0 is moved right 1 and up 2, it's going to go here. If you take negative 1, 1, and you go right 1 and up 2, it's at 0, 3. If you take the negative 4, 2, and you go right 1 and up 2, it's got negative 3, 6. Negative 3, 4, excuse me. And there's our graph, which your calculator can easily verify. But this is not a calculator assignment. If you did this problem set with a calculator handy, a graphing utility, you kind of did it all wrong. Okay? You really did, because on my test you're going to have to do this in stages. If I see a table, then I know you're just plugging in numbers, which is fine, but I will look for stages. Okay? To see why.